Hello. In this video, we are going to solve homogeneous linear systems of differential equations with constant coefficients that have complex eigenvalues. All right, so let's just jump in with an example. So let's say we had x prime and our matrix that represents our system is as follows. Okay, so we start off solving the system the same way that we did for systems that did not have complex eigenvalues. You go ahead and just say that let x equal xi e to the rt. As a consequence, you get x prime equals xi r e to the rt. We take these and plug them in. We get xi r e to the rt equals our matrix times xi e to the rt. The e to the rt's cancel. And this equation that's left, okay, we do have variables here. There's an r that's unknown. There's a xi that's unknown. And so what we want to do is we want to go through and find the xi and the r that makes this true. And this is the eigenvalue eigenvector problem. So to go through and solve this, we want to move these to the same side and then combine them. And if you do that, what you end up with is -1/2 minus r1, -1, -1/2 minus r times xi equals 0. All right, and to see the steps to get from here to here, you'll have to go and watch the previous video on a more general homogeneous linear systems of differential equations with constant coefficients problems. Okay, so once you get to this point, what we want to know is we want to know the r that will make it so that this system has solutions other than xi equals 0. That's going to occur when the determinant of this 2x2 matrix equals 0. So normally if you have a system, you're looking for where the determinant is not equal to 0. But in this case, we're looking for where the determinant equals 0 because we want to have non-zero solutions for xi. If the determinant is not equal to 0, then xi would be forced to be 0. And if we multiply this out, we get -1/2 minus r times -1/2 minus r plus 1 equals 0. And if we expand that, we get r squared plus 1/2 plus 1/2, so we get plus r plus 1/4 plus 1, so plus 5/4. And then we can go through and solve this using the quadratic formula. And so we're going to get 1 minus 5, so it's going to be -4. The square root of -4 is going to give us plus or minus 2i. Okay, and so this is the issue right here, right? So in the last section where we went through and solved more general homogeneous linear systems of differential equations with constant coefficients, you didn't get complex eigenvalues, right? So in this case, we got a complex number. And so what do we do about that? Okay, so at first you go ahead and you just start off doing the normal thing. You don't do anything differently than we did in the last video. We just go ahead and just jump in, take our eigenvalue, plug it in, and try and find the corresponding eigenvectors. All right, so what we're going to do is we're going to focus on the plus case here. We're going to do -1/2 plus I. So we'll let our eigenvalue be -1/2 plus I. and then see what the consequences of that are. So if you plug in -1/2 plus I, what are we going to get in our, in our equation here? All right, so we're going to we'll have -1 minus, and then in parentheses, -1/2 plus I. And then we still have 1. And then -1. And then the same thing again. Okay, and then we can simplify this. 1/2, we got plus another 1/2. So we're going to have 1 minus I. Oops, did I copy that wrong? Yes, I did. That should be a -1/2. There we go. So we're going to have -I, -1, 1, -I. And then to go through and solve this system, we're going to shift it over to a augmented matrix. And then you can go through and row reduce this. We're going to get 1, I, 0, and then an all 0 row, and go through and check that. And then at this point, we're now going to shift it back to a system format where these are coefficients. So we'll have xi1 plus I xi2, 1 being the coefficient for xi1, I being the coefficient for xi2 equals 0. And then we have a free variable from the all 0 row. We get xi2 equals xi2. And then if you move the xi1, get the xi1 by itself, you get negative I xi2. And then xi2 equals xi2. And so we get xi equals negative I1 times xi2. Okay, and so this would be our eigenvector. One thing we can do to go through and simplify this, which I've seen in some places, is to go through and get a 1 in the top here. To get a 1 in the top here, you would multiply by I over I. So you could go through and rewrite this as 1 and then I. And then, we'll just, I don't know, we'll put times t to go through and represent the fact that we're replacing xi2 with I times t. And so this gives us an alternate eigenvector, which may be a bit simpler. And these are multiples of each other, right? Anytime you get an eigenvector, you can always go through and multiply it, by, you can always do multiples of it, scalar multiples, or I guess in this case, I multiples. I'm not sure exactly how that works, but the idea, as long as you multiply the top and bottom by the same thing, then you're okay. Okay, so now we have the eigenvalue and the eigenvector. And so now we can go through and take those two, put them together, and we get our first solution. Okay, and so where does that come from? If you're a little bit lost here, right? So got to go back. So what did we do? We said we let x equal this. This is basically kind of like what a guess is as far as our solution was. And then we just need to know what the xi and the r to plug in for that to make that, to get a solution there. And so that's what we just did. We went through and we found the r, that was this, the eigenvalue. And then we found the xi, that's this. That was the process that we just went through. So we've got r and xi. So we just take those and plug them into our guess as far as what the solution will be, and it looks like this. Okay, so everything so far really has been the same as from the last video where we went through and solved systems of differential equations with constant coefficients. So this is where things change, right? So this is not an acceptable solution. We started off with a system of equations that had no complex numbers, everything was real, and we ended up with a solution that was complex. So we want to go through and find a way to take this and rewrite it into a format that doesn't have complex numbers. And the secret to doing that is the same as the secret from earlier in the course back in second order differential equations. We want to go through and use Euler's formula. All right, so let's do that now. And how do we do that? So to use Euler's formula, you first have to split this apart. And so we're going to get e to the negative 1/2 t times e to the it. So Euler's formula allows us to replace e to the it with cosine t plus I sine t. All right, and then once we've done that, we can actually go through and multiply this out. By multiply, I'm going to take this, and I'm going to multiply it by this, and I'm going to multiply it by this. So when we do that, you're going to get e to the negative 1/2 t cosine t plus I e to the negative 1/2 t sine t. And I'm going to do the same thing for the denominator. So we're going to do this times this times this. So that will give us I e to the negative 1/2 t cosine t minus e to the negative 1/2 t sine t. Okay, and from there we got I times I gives us I squared, which is -1. And so that's where that negative came from. And then at that point, I'm going to go through and I'm going to split this up into two solutions. All right, so I'm going to put the non-I parts here in the first. And the second one will have the I parts. And so we end up with this structure for the solution where we have this, which is the real part, and we have this, which is the imaginary part. So in a previous video, we said that if we went through and solved a system of differential equations, in general, doesn't have to be have constant coefficients, but in general, if you solve a system of differential equations that starts off with all real stuff, and you end up with a complex solution, then both the real part and the complex part, the real part and the imaginary part are both solutions. So what we can say from here is we can say that this is a solution to the differential equation. So that, what does that mean? That means if you took this and you plugged it into this, it would make it true. And that also this is a solution as well. So we could take this and plug it in, and it would also make the differential equation true. In which case we have two separate solutions here. And so while I have an x1 here, I'm actually going to take x1 and redefine it and say, well, you know what, how about instead we'll have x1 be this solution, e to the negative 1/2 t cosine t negative e to the negative 1/2 t. Oop, I think that should be a sine t. Yeah, let's copy that. Sine t, and then we get x2 equals our other solution, e to the negative 1/2 t sine t. And so now we've got two solutions, and then the only thing left to check is, are these two solutions different enough that we can go through and we could say that we have all the solutions? To figure that out, you need to go through and calculate the Wronskian. So if we calculate the Wronskian for x1 and x2, to do that, we would need to calculate the determinant of the 2x2 matrix that's made up of these two solutions, where these form the column vectors. So we want to take our first guy here. All right, and then we can go through and calculate the determinant. So we take this times this. That's going to get us e to the negative t cosine squared t. And then minus this times this. We're going to get double negatives. They go to plus e to the negative t sine squared t. And then you've got sine squared plus cosine squared is 1. So we can pull that out and you get e to the negative t. And then this is not equal to 0. All right, so since this is not equal to 0, that tells us that these two vectors are linearly independent. And if they're linearly independent, then they're different enough that they will get us all the solutions to, the linear combinations will get us all the solutions to the differential equation. And so we can go through from there and say that the solution is C1 times the first one, which we can go ahead and actually pull out e to the negative t here and write this as cosine t negative sine t plus C2 e to the negative t sine t cosine t. Okay, and then that's our solution to the differential equation. All right, now, just like in the last video, we can go through and try and create a graph of this, a phase portrait. So to do that, we're going to follow some steps like the ones we did in the last video. It's going to be a little bit different. We're going to start off by, we'll set C2 equal to 0. So that's the same. So to create the phase portrait, we'll start off by setting C2 equal to 0. And if we do that, we get x, which is x1, x2, which equals C1. Actually, I'm going to multiply this back through. So we're going to have C1 e to the negative t cosine t. Right? That's this times that. And then for the bottom, this times that. Okay. And then next we'll go through and set x1 equal to C1 e to the negative t cosine t, and x2 equals negative C1 e to the negative t sine t. All right, and then this is a parametric equation that's in x1 and x2. And so when you have parametric equations with sines and cosines like this, you want to go through and use the identity, the trig identity, right, to try and figure out what the structure is between them. And so to do that, we could go through and we could solve for sine here and then substitute in. So sine t is going to equal x2 over negative c1 e to the negative t. So we're going to have x2 over negative c1 e to the negative t squared. And then cosine will be that's x2, and then cosine will be x1 over c1 e to the negative t. All right, and then we can go through and simplify this. This is x1 squared over c1 squared e to the negative 2t, and x2 squared over c1 squared e to the negative 2t equals 1. Take this, multiply to the other side. We get x1 squared plus x2 squared equals c1 squared e to the negative 2t. All right, and that's enough for us to go through and have some idea of what this looks like. All right, so we have the phase portrait is in the x2 is in an x1 x2 axis. It's where we graph it. And so what we have is x1 squared plus x2 squared. So that's our circle structure. Maybe it looks a little weird because you're used to seeing x squared plus y squared. But in this case, we have x1 and x2 instead of x and y. So this is our circle structure. And it's saying that we have a circle type structure that is equal to c1 squared, which is just some constant. It just represents the c1, which so it could be as small as 0, which would mean that we would be right at the origin. Or it could be significantly larger. And then e to the negative 2t, what is this? What's the effect of this? So the parameter is still in there. And the effect of that parameter is that it's going to change the radius over time, and it's going to make the radius smaller as t gets larger. Okay. So as t gets larger, we'll move toward the origin. All right, so we want a circle structure that changes over time, that goes toward the origin. And if you think about what that would look like, if you combined all those traits, that's going to look like a spiral. So the only question is what type of spiral do we have? Do we have a spiral that looks, like that? Or do we have a spiral that does the opposite, that looks like that? All right, and so to go through and figure out which one is which, what you can do, probably the easiest thing to do would be to go through and we can just plug in a value to this. So if you go through, and by that I mean, if you go through and you plug in, say, t equals 0 and say t equals pi over 2, then that can help you to figure that out. And then that's just a classic method to figure out whether you've got kind of clockwise or counterclockwise, which if you go back and look at those spirals that I drew, one of them spiraled out in a clockwise way and one of them spiraled out in a counterclockwise way. So that's really the question, is do we have clockwise or counterclockwise? So you go ahead and just take 0 and plug it in, and we're just going to ignore c1. We'll say c1 is 1. If you go through and plug in 0 into this, so we're going to get 1 for cosine then, and we'll get 1 for e to the negative 0 here. And so we'll get x1 is 1 when t is 0. So we'll just say that puts us right here. And then if you go through and do the same thing for x2, you get 0. So that's this that's this point right there, as I was saying. And then we could go ahead and plug in pi over 2. Plug in pi over 2. So when we plug in pi over 2, cosine of pi over 2 is going to be 0. Sine of pi over 2 is going to be 1. So now x2 is going to have the 1. However, you got to keep in mind that we're plugging pi over 2 into the exponential term here as well. And e to the negative pi over 2 is going to be a smaller number than e to the 0, right? As t increases, you get smaller values for these exponential functions. And so because of that, if this is the point that represents 1 and 0, then we're going to have a smaller point that's closer to the origin when we have e to the negative pi over 2 times 0 and e to the negative pi over 2 times 1 from there. And so what this tells us is that if this is where t was 0, and this is where t was negative, this was where t was pi over 2, then as we're spiraling inward, so first of all, we're going in this direction as t increases, and we're going in toward the origin. So that kind of tells you what you need to know about how the spiral behaves. Okay. And so from there, that's our first solution. And so you can say, okay, what do I need to go through and do all that for the second solution? Not really. If you get a spiral for one of them, you're going to get a spiral for the other as well. And the orientation of the spirals needs to be the same. Otherwise, the solutions are going to intersect each other, which is not possible. And so because of that, we could go through and we know that the other solution is going to look some variation of that. It's going to look something like that. And so what we have is we have spirals for our solutions, and certainly 2 is sufficient. You don't need to draw a bunch more than that to see what they look like. So the phase portrait for how the solutions behave are going to be spirals. Oh, and then one final thing is that you should go ahead and put arrows on these to represent the fact that you're going in toward the origin as opposed to coming out. I'd say 1 is enough. Okay, so that goes through and gives us our solution to our first example problem. Let's go through and do another example. All right, so we start off just like normal. We go ahead and let x equal xi e to the rt, then x prime will equal xi r e to the rt. Take those, substitute them in. Xi r e to the rt equals our matrix times xi e to the rt. E to the rt's cancel. This is the eigenvalue eigenvector problem. We want the determinant. Equals 0. Multiply this out. We're going to get 1 minus r. Negative 3 minus r. Plus 5 equals 0. The r squared. Got positive 3r minus r. So that's going to be plus 2r. Minus 3 plus 5. So we get plus 2 equals 0. Quadratic formula. Four minus 8, we're going to have 2i from that. All right. Take r equals negative 1 plus I. Plug that in. What do we got here? So we're plugging it in, plug it in here. So we're going to have 1 minus negative 1 plus I. Oops, hold on. That should be 1 minus positive 1. 1 plus I. There we go. All right, and then what do we got? We got 5 at below that. And then next we've got -1. And then -3. All right, and then so we can simplify that. Two minus I, 5, -1, -2 minus I. All right, and then we're going to shift over to our augmented matrix now. And we're going to go ahead and put this into reduced row echelon form. So we're going to get 1 minus 2/5 minus 1/5 I, 0, and then we'll have an all 0 row. And then we translate over to a system format. The augment. This is the coefficient of xi1, coefficient of xi2. And then we get xi equals and then from there, so, and to get that, you just take this, move it to the other side, and that's going to why you get a positive version of that. And then so to clean this up, what you can do is you can go through and you can get rid of the fractions by multiplying top and bottom by 5. And we'll replace, since we've multiplied this by 5, we'll replace it with a t. Okay. And then so next we go ahead and take our eigenvalue and we take our eigenvector and we go ahead and plug them in. What did we get again? So we got 2 plus I. And our eigenvalue is -1 plus I. All right, and then next, just like before, we want to go through and use Euler's formula. And then just like before, we want to multiply this out. So take this, multiply it by 2 plus I. We're going to have 2 times e to the negative t times cosine t. 2 times e to the negative t times I sine t. And I times e to the negative t cosine t. I e to the negative t I sine t. And 5. And so on. All right, and then last, we need to split this up into real parts and complex parts. So here, this is a real part. This is a real part. That's a real part. Imaginary. And then our last piece there. No negatives. So we've got a real part plus a imaginary part. And again, we know that we can, if we have a solution to a system that's in complex form like this, that both the real part and the imaginary part both solve the differential equation. So we can grab these and say that this guy is x1, this guy is x2, and then we just need to calculate the Wronskian to go through and show that they're different enough. Oops. No vector format. All right, so what we got? 2 e to the negative t cosine t. Minus e to the negative t sine t. 5 e to the negative t cosine t. 2 e to the negative t sine t. Plus e to the negative t cosine t. Sorry, there's a menu in the way that's blocking me from putting this in line with that one. And then finally 5 sine t. 5 e to the negative t sine t. Get the e to the negative t. Yeah, I did. Okay, that's funny. All right. And then we can go ahead and calculate the determinant of that. So we're going to have this times this. So we'll distribute 5 e to the negative t sine t times, so we're going to have 10 e to the negative 2t sine t cosine t, and then minus 5 e to the negative 2t sine squared t, and then minus, then this times this, we're going to have 10 e to the negative 2t sine t cosine t, and then minus, then this times this, we'll have 5 e to the negative 2t cosine squared t. These cancel. Sine squared plus cosine squared is 1, so we're going to have negative 5 e to the negative 2t, which is not equal to 0. So these are sufficiently different that they will satisfy they're linearly independent, which means that they're sufficiently different that we will be able to find all solutions to the differential equation by taking linear combinations of them. So we can say that the solution is going to be C1. We could factor out the e to the negative t here times 2 cosine t minus sine t over 5 cosine t plus C2 e to the negative t times 2 sine t plus cosine t, and then 5 sine t. Okay, so there we go. And that's how you go through and solve that guy. So that's the solution to that system of differential equations. All right. And then to go through and do the phase portrait, this is going to start off similar to the last one, but we're going to discover that there's a little problem. Let's go ahead and figure out what that problem is. So we'll start off, we'll say let C2 equal 0. That means we have x equals x1, x2, which equals, and if you were to multiply all these out, you're going to get C1 e to the negative t cosine, t? 2 cosine t. Yeah, we'll throw a 2 there. And then minus sine t. So we're going to have minus C1 e to the negative t sine t. And then for the bottom, we'll have C1, 5 C1 e to the negative t cosine t. And so putting this together, we get x1 equals 2c1 e to the negative t cosine t minus c1 e to the negative t sine t, and x2 equals 5c1 e to the negative t cosine t. All right, so last time this happened, in the last problem, we went through and said, oh, hey, we've got parametric equation, we've got sines and cosines, so we could go through and use the identity. All right, so you could go through and you could do sine squared t plus cosine squared t equals 1. You can't do that this time. Why? Why can't you do that? Because of this extra cosine. This extra cosine basically wrecks everything. So you can't go through and graph this parametric equation, in that way. All right, so that's not possible. So what can you do instead? So what you can do is that this is just a parametric equation. It's a very, very complicated one, but we could go through and use a parametric equation plotter, like a graphing tool, to go through and get us a sketch of what this looks like, and then we could use that sketch to figure out what the phase portrait's going to look like. Okay, so let's just jump out and take a look at so I've already gone through and plotted this guy. Actually, hold up 1 second. All right, I had to quickly fix a little minor problem. So here is a parametric equation plotter. And so we've gone through and just taken our differential equation, our parametric equation, and we've plugged it in for x and y in this case. So that's a little bit different, of course, right? So we've got x2 and x1. And if you take a look at the picture here, it kind of gives you an idea of what this looks like, right? So we can zoom in. All right, and so it does look like a spiral. So we're still getting a spiral format here. Okay, because of the negative, that tells us that it does go into the origin. You can see that actually as well if you start moving here. So as we increase, right? So if we start off here and we increase t, then we see it move toward the origin there. Okay, and so it's the same general idea. It's just the spiral is more complicated because of the fact that we have that extra sine term. All right, and so we can just kind of do a very quick and dirty sketch. If I can jump back in. So we can just do a quick and dirty sketch. Right, and so it looked something like, right, so we still had a spiral, but it was just not a perfect circle, right? So in our last case, it was a perfect circle, whereas this time we have kind of a something a little bit less than perfect, right? It's kind of elliptical and it's rotated. So that's I kind of tried to represent that in the picture here. But anyway, so that's the first solution. If you went through and did the second solution, it should look similar. And so we could kind of just go through and just draw a second spiral, that looks kind of like that. And then these are going toward the origin. All right, and so I don't know, maybe we could try that one more time. It didn't really exaggerate it quite enough. So it was really kind of more like, I guess it doesn't really look any different. Anyway, you get the idea. And then we can go through and draw a second one. And yeah, these are going to the origin. All right, so I did go through and do one more quick example. So we've got one example where you end up with a perfect circle. That's the first example. We've got one example where you don't end up with a perfect circle. That's the second example. And then there actually is, or I guess these are both spirals, but there is one more case. And so I'm going to go through it quickly here so you can see the last possibility. So we start off the same. Plug in. The RTs cancel. This is the eigenvalue eigenvector problem. We can rewrite it. We want the determinant to equal 0. Multiply this out. So we've got plus 2r, minus 2r. So those cancel. Then we have minus 4 plus 5. So that's plus 1. And so we get r equals plus or minus I. All right, so notice there's no real part. That's going to have an interesting effect. And so that's what I wanted to show you with this last example. All right, so we're gonna go with a plus I. All right, equals I. So take that, plug it in. So we're gonna get 2 minus I, negative 5, 1, negative 2 minus I. All right, and then we want to go through and row reduce. All right, and then next we will translate back to a system form. We have our free variable. Move this to the other side, and that will get us xi. We'll have 2 plus I and 1. All right, and then that tells us that our first solution is going to equal times e to the it. So there's no There's the only t component is the imaginary part. So we're missing that real part. All right, so what is that going to mean? That's going to mean there's not going to be an e to the t after we go through and simplify this. All right, so we go through and to simplify this, we're going to use Euler's formula. So that doesn't change. Take this, multiply it out. We're going to get 2 cosine t plus I cosine t plus 2i sine t minus sine t cosine t plus I sine t. And then we can split this up. 2 cosine t minus sine t cosine t plus I cosine t plus 2 sine t sine t. All right, we've got our two solutions here. All right, and then we can go through and use the Wronskian to check them. All right, so what do we got here? So this is the first one. We got 2 cosine t minus sine t. Over cosine t. And then for the second one, cosine plus 2 sine. Sine t. And if we multiply these out, calculate the determinant. There should be a determinant in here somewhere. There we go. Take this times this. So we're going to get 2 sine t cosine t minus sine squared t. And then minus this times this. So we're going to have minus cosine squared t. And then minus 2 sine t cosine t. These cancel. And sine squared plus cosine squared is 1, so this equals -1, which is not 0. So our two solutions are sufficiently different that they do get us, the linear combinations get us all the solutions. And so that's the linear combination of our two solutions. So next we want to go through and sketch this, and we're going to have the same problem that we did on the last one. Anytime you've got more than just sine and cosine in our vector components here, our xi portion of the solution, that's going to make it so that we can't go through and use the method that I showed earlier in this lecture for graphing it. You're going to have to use a parametric equation plotter. All right, but we can go through and we could say, let's see, 2 equals 0. If you did that, you're going to have x equals x1, x2, which is going to equal C1 times this. So we're going to have 2C1 cosine t minus 2C1 sine t. And C1 cosine t. All right, did I copy that right? We've got two. Oh, I added an extra 2 in there. Okay, and then we're going to get x1 would equal C1 times we can just get rid of that. We just ignore that C1. So the C1 is just it just says that whatever we end up getting is going to scale. So I'll talk about the effect of that in a second. So we're going to ignore it when it comes to going through and looking at our plotter anyway. But we'll talk about what that C1 is going to do in a second. All right, so this is what we end up with. You can't go through, you could try, oh, well, I want to use sine squared plus cosine squared equals 1 to go through and you know, find the structure in this. And the thing that you're going to discover, oh, you got this extra cosine here that's going to stop you from doing that. So the only thing we can do is we can go to our parametric plotter. So let's jump over to that and see what this looks like. So we just took this and plugged it in without the C1. All right, and that's not the right one. There's the right one. So if you plug it in, this is what you end up getting. And so the effect that that C1 has is it's going to scale this. So what it's going to mean is if you went through and took the, each of these and multiplied them by the same scalar. So if we went through and doubled both of these or tripled both of these, multiplied both of them by 5, that's the effect that that C1 has, is that it gets us all multiples of this. And if you do that, what you're going to get is you're going to get a bigger and bigger version of this. Okay, so if you multiplied this by 2, it will make it twice. Well, maybe not. I don't know if it's exactly twice as big, but you're going to have points that are twice as far from the origin. And if you multiply it by 5 and so on. Okay, so that's what the effect of that C1 is, that it goes through and it scales this. The other thing we can look at while we're here, what direction does this go? All right, so as we increase T, we go counterclockwise. So positive T goes counterclockwise, and we have this elliptical rotated shape. So it's kind of the same thing as the last example, except not a spiral. Okay, so instead of being an elliptical spiral, we're going to have an elliptical circle. All right, so let's jump back in. And so the way we could sketch this, we had something like that. We said the rotation was this way, and then we could just draw bigger and bigger versions of that to represent the other solutions. Okay, and that's it. And again, just like with the earlier examples, you don't need to go to the second solution and graph that. It should look similar. Okay, so that's how to go through and solve homogeneous linear systems of differential equations with constant coefficients that have complex eigenvalues. All right, so thank you for watching. See you next time.